Okay, in this video we're going to be talking about angles of polygons. Now you recall a polygon is just a figure formed by three or more coplanar segments that we call sides. Well, in this particular section we're going to be looking at a particular type of polygon which is called convex polygons. Now in convex polygons all of the vertices of the polygon point outward. So for example, all the vertices point outward. That might be an example of a convex polygon. If you have a polygon where all of the vertices, or where at least one of the vertices points inward, like maybe like that, this is called a concave polygon. And we're not going to be dealing with concave polygons. We're just going to be talking about convex polygons. So the main thing that we want to look at in this section is some properties of the angles of convex polygons. So you have a table there in your notes, and I want you to fill in these different types of polygons in that second column there where it says names. So we're going to have a triangle, a quadrilateral, pentagon, hexagon, heptagon, and octagon. And in that second column you can fill in the number of sides for each one of these types of convex polygons. So a triangle has 3 sides, quadrilateral 4, pentagon 5, hexagon 6, heptagon 7, and an octagon 8. And now over in the other column over here, you've got room to draw a little picture of each one of the polygons. We're gonna fill those in just a minute. And the first thing I want to talk about here is the number of triangles inside each type of convex polygon. Now, for a triangle, that's not that difficult. When you talk about a triangle, you're just talking about one triangle. Now, if you talk about a quadrilateral, and here I want to draw a picture of a quadrilateral, and it can be just any particular shape as long as it has 4 sides. So here's a picture of a quadrilateral. It's got 4 sides, and when I talk about the number of triangles in this quadrilateral, what I mean is if I pick one vertex of my quadrilateral, and if I draw a diagonal to all of the opposite vertices that I can draw a diagonal to, then I'm going to divide my polygon here into some number of triangles. And you can see for a quadrilateral, I can divide that quadrilateral up into 2 triangles, this one on the top and this one on the bottom. So for quadrilateral, a 4-sided polygon, I can divide that into 2 triangles. Notice I'm drawing all of my diagonals from the same vertex point. All right. So I want to do that for each one of my other convex polygons here. For a pentagon, which has 5 sides, 1, 2, 3, 4, 5. I want to see how many triangles can I draw from one of my vertices. So let me pick this vertex. So there's a diagonal, and that's all I can draw. So I've got 1, 2, 3 triangles that I can draw inside a pentagon. Hexagon is 6 sides, 1, 2, 3, 4, 5, 6. Let's do the same thing. And I'm going to divide that one. Let's see, I've got 1, 2, 3, 4 triangles that a hexagon can be divided up into. And you might be able to see where this is going. For each one of my convex polygons, the number of triangles that I can divide that convex polygon into, it's always 2 less than the number of sides. So I could draw a picture of a heptagon with 7 sides, and for a heptagon, I'm going to be able to divide that into 5 triangles. For an octagon, I'm going to be able to divide that into 6 triangles, and you could go on and on and on for however many, however large a polygon you wanted to make. All right. Now, the next thing I want to look at is the sum of all of the interior angles of each one of these convex polygons. And if we start with a triangle, which we're familiar with, let me put a triangle up here. So we're already familiar with a triangle and with the sum of the interior angles of a triangle. We know the sum of the interior angles of a triangle is always 180 degrees. So if I have just one triangle, sum of all its interior angles is 180 degrees. Well, if I happen to have 2 triangles, which is what I have if I divide up my quadrilateral into triangles, then the sum of all of my interior angles is going to be the sum of all the interior angles of this triangle and the sum of all the interior angles of that triangle, which is going to be 2 times 180 degrees, or 360 degrees, right? So just say 2 times 180 degrees equals 360 degrees. For a pentagon I can divide up into 3 triangles. Each triangle has 180 degrees of interior angles. If I multiply that times all 3 of the triangles in my pentagon, then I get 3 times 180, which is 540 degrees. And you can keep on going with each one of the remaining convex polygons here. For a hexagon, I divide a hexagon into 4 triangles, which means I've got a total of 4 times 180, or 720 degrees is the total of all of my interior angles. Heptagon, 5 triangles, 5 times 180 is 900 degrees. And an octagon, 6 triangles, 6 times 180 is 1080 degrees. And again, you could keep going. So what we see here is kind of an illustration of what we're going to call the interior angle sum theorem. And the interior angle sum theorem just says if a convex polygon has n sides, then the sum of the measures of all of its interior angles is n minus 2 times 180 degrees. And that's what we see here. The sum of all the interior angles of each one of these convex polygons is just the number of sides in the polygon minus 2, and then you multiply that times 180 degrees. So let's take a look at some problems that we can solve using this information that we now have on angles of convex polygons. So example number 1, find the sum of the measures of all of the interior angles for these different polygons. Now here we have a nonagon and a decagon. A nonagon is just a word for a 9-sided polygon. And since I know how many sides it has, I know how many triangles I can divide that 9-sided polygon into. Since it's got 9 sides, it's going to have 9 minus 2, or 7 triangles. 7 times 180 degrees for each triangle is 7 times 180, 1,260 degrees. So 1,260 degrees, that's the measure of all of the interior angles of a nonagon. Decagon, that's 10 sides. I'm going to use my handy formula that I've got, n minus 2, which would be 10 minus 2 times 180, which is 8 times 180. And 8 times 180 is 1,440 degrees. And I could go on with all the rest of these. For a 12gon, that's a 12-sided figure. Once you get above a certain point, you kind of stop giving them individual names and you just call them a number by however many sides they have. So a 12gon has 12 sides. I'm going to calculate that as 12 minus 2 times 180, which is 10 times 180, which, 10 times 180, which is 1,800 degrees. 27gon, 27 minus 2 times 180, which is 25 times 180, which is 4,500 degrees. Now, example number 2, I've got a quadrilateral, PQRS, and I'm asked to find the value of x. Well, I can take what I know about quadrilaterals, and in particular I can take what I know about the sum of the interior angles of quadrilateral. Remember that for a quadrilateral you can divide that into 2 triangles, and if you add up the sum of the interior angles of those 2 triangles, I remember that the total interior angles in a quadrilateral is going to be 360 degrees. So 360 degrees equals the sum of all 4 of these interior angles. So I can just add these up and set up an equation that I can solve. So 360 degrees must be equal to x plus 134 plus 73 plus 82. And if I do a little bit of arithmetic, then I get this is equal to 289. And if I subtract 289 from both sides of my equation here, then I get x is equal to 71. For example number 3, it says given hexagon HEXAGN, find the value of x and the measure of each interior angle. Well, once again, I'm going to use what I know about the sum of the interior angles of a hexagon. If I divided my hexagon into triangles, I have 1, 2, 3, 4 triangles, which means that the total measure of all the interior angles of my hexagon is going to be 180 times my 4 triangles, which is 720 degrees. So I can set up my equation. 720 degrees is the total of all of the interior angles. So 4x plus 4x plus 2x plus 4x plus 3x plus 3x. So I have 720 equals 20x, and I divide both sides by 20, and I get x equals 36. Now, once I know the value of x, I can go back and plug x in for each one of the individual angles, and I can find the value of each angle. So 4 times 36 is going to be 144. 2 times 36 is 72. 4 times x is 144. 3 times x is 108, and 3 times x is 108. All right, now we want to talk about a particular type of convex polygon, which is called a regular polygon. And a regular polygon is a convex polygon that is both equilateral and equiangular. Now, we've talked about equilateral figures before. In fact, we've done a lot with equilateral triangles. And equilateral triangle is just a triangle that has all sides congruent. Well, equiangular is similar in that equiangular is just a fancy word for all angles are congruent. So we have if we want to fill in kind of the same type of table that we filled in before, except now all of our polygons that we're talking about here are regular polygons. Well, for each one of these regular polygons, the number of sides is going to be the same. A triangle, a regular triangle has 3 sides. A regular quadrilateral has 4 sides. By the way, a regular quadrilateral is more often referred to as a square. In other words, it has 4 sides. The 4 sides are all the same, and the 4 angles are all the same. A triangle that has it's a regular triangle is usually called an equilateral triangle. Equilateral. A regular pentagon, 5 sides. Hexagon is 6. Heptagon is 7. Octagon is 8. The number of angles for each one of these regular polygons is exactly the same as the number of sides. So 3, 4, 5, 6, 7, and 8. And the sum of all of the interior angles for a regular polygon is going to be the same as the sum of all the interior angles of a non-regular polygon. Well, we just calculated all those, sum of all the interior angles, in that previous table. So we can just fill those in. So let's see, this one is 180, 360, 540, 720, 900, and 1080. So now you may be saying to yourself at this point, well, isn't this kind of a waste of time? I mean, we already filled in all these numbers in that previous table. Well, we did all this because there's this final column over here that we didn't have in the previous table. And in fact, we couldn't have it in the previous table because in the previous table, we weren't talking about regular polygons. In fact, we were talking about polygons in which all of the different interior angles could be different. So it wouldn't make any sense to talk about the measure of only one interior angle because we wouldn't have any way of knowing how to calculate that measure. Well, for a regular polygon, all of the angles are the same. Well, since all of the angles are the same, if I have a regular polygon that has 3 angles, like if it's a triangle, and since I know the sum of all those interior angles is 180, I know the measure of just one is 60 degrees. And in fact, we've used that property quite a bit already when we're dealing with equilateral triangles. Well, that's just a way of saying that 180, if I take 180 degrees and divide it by 3, the number of angles, that gives me the measure of just one of the angles. Well, if I take a quadrilateral, a regular quadrilateral, that is a square, I know it has 4 interior angles. I know the sum of all 4 of those interior angles is 360 degrees. Once again, if I just divide 360 by 4, that's going to give me the measure of one of those interior angles, which is 90 degrees. And I'm going to do the same thing for each one of the rest of these. The total number of angles of a pentagon is 5. The sum of all the interior angles is 540. Since all of the angles, since it's a regular pentagon, all of the angles are the same measure, so I can just say 540 divided by 5, and that gives me 108 degrees, the measure of one interior angle. For a hexagon, measure of all the angles is 720. Total number of angles is 6. 720 divided by 6 is 120. For a heptagon, sum of all of the interior angles is 900. Total number of angles is 7. And since all of the angles are equal, 900 divided by 7 is 128.57 degrees approximately. For an octagon, sum of all the interior angles is 1080. I've got a total of 8 equal angles, so 1080 divided by 8 is 135 degrees. All right, now, one of the things that we can use that information for is to talk about the exterior angle measures of regular convex polygons. So let's take a look at just these 4 types of regular polygon: a regular triangle, a regular quadrilateral or a square, a regular pentagon, and a regular hexagon. So the measure of one interior angle of a regular triangle, that is an equilateral triangle, is 60 degrees. The measure of one interior angle of a regular quadrilateral or a square is 90 degrees. The measure of one interior angle of a regular pentagon, let's see, we just calculated that, that's 108 degrees. And the measure of one interior angle of a hexagon, we calculated that as well, 120 degrees. Now, if I want to calculate the measure of one of the exterior angles, remember an exterior angle, if I draw that in my picture here, an exterior angle is an angle that forms a linear pair with one of the interior angles of my figure. So if my interior angle here is 60 degrees, well, this exterior angle must be 120 degrees. If this interior angle is 90 degrees, that exterior angle must be 90 degrees. If this interior angle is 108 degrees, then that exterior angle must be 72 degrees, 180 minus 108. And if this interior angle is 120 degrees, then this one must be, the exterior angle must be 60 degrees. Now, the number of sides, I already know the number of sides of each one of these regular polygons. 3 for a triangle, 4 for a quadrilateral, 5, and 6. Now, what I want to do here is, I want to talk about the sum of all of the exterior angles. And when I'm talking about the sum of all of the exterior angles, in this case, when I say all, what I mean specifically is one exterior angle at each vertex. All right, so in other words, for a regular triangle, I want one exterior angle at this vertex, and I want one exterior angle at this vertex, and I want one exterior angle at this vertex. All right, so I'm going to have a total of 3 exterior angles, all right, or the same number of exterior angles as I have sides in the figure. Same thing for here. I've got one exterior angle here, one exterior angle here, one here, and one here. All right? So the sum of all of the exterior angles, if I have 120 exterior angles on this three-sided polygon, my triangle, and if each exterior angle is 120 degrees, I've got 3 of them, then the sum of all of them is going to be 120 times 3, or 360 degrees. If I have a total of 4 exterior angles on this 4-sided regular polygon, and each exterior angle is 90 degrees, then the sum of all of the exterior angles is going to be 90 times 4, which is 360 degrees. And you may start to see where this is going. If I've got a 5-sided regular polygon, that means it has 5 exterior angles. If each exterior angle is 72 degrees, then the sum of all of the exterior angles is 72 degrees times 5, which is 360 degrees. A hexagon has 6 exterior angles. Each one is 60 degrees. 60 degrees times 6 is 360 degrees. So what you can see here is that it doesn't matter what type of convex polygon I have here, the sum of all of the exterior angles, if I have just one exterior angle at each vertex, the sum of all those exterior angles is always going to be 360. Well, this is a pretty handy property for us, and it leads us to what we're going to call the exterior angle sum theorem. For any convex polygon, the sum of the measures of the exterior angles, one exterior angle at each vertex, is always 360 degrees. Now, for a regular polygon, which is the polygons that we were just looking at in the table, for a regular polygon, this has an even more useful property, which is that the number of sides in the regular polygon times, not the number of sides. Let's write it like this. The measure of one exterior angle of the polygon times n, where n is the number of sides, is always equal to 360. And this turns out to be a formula that's pretty handy, because if I happen to know, for example, the number of sides in a regular polygon, well, then I can use this formula to tell you the measure of one exterior angle. Or if I happen to know the measure of one exterior angle in a regular polygon, then I can use this formula to tell you the number of sides in that regular polygon. So let's take a look at how we might use this formula in a couple of examples. So example number 4. For a regular octagon, find the measure of each interior and exterior angle. So I'm going to start with this exterior angle right here. And I'm going to use the fact that since this is a regular octagon, I know I can use this formula that we just came up with on the last slide, which is to say one exterior angle times n equals 360 degrees. Well, in this case, n, which is the number of sides of my polygon, since it's an octagon, I've got 8 sides. So one exterior angle times 8 equals 360 degrees. Well, if I divide both sides of my equation here by 8, then I've got one exterior angle equals 360 divided by 8, and 360 divided by 8 is 45 degrees. So I just found the measure of an exterior angle of my octagon. That's this angle right here. Now all I have left is to find the measure of an interior angle. Well, my interior angle is this angle here, which forms a linear pair with that exterior angle, which means all I need to do is subtract 45 from 180, and 45 subtracted from 180 is 135. So now I know my interior angle of my regular octagon. Now, example number 5. Says, given that 60 degrees is the measure of an exterior angle of a regular polygon, find the number of sides. All right, so this one is similar to example number 4, except it kind of goes in the opposite direction. So let's say I draw a picture here. I've got some regular polygon, but I don't know how many sides it has. So let me draw a picture of some kind of regular polygon. I don't know how many sides it has, so I'm just going to kind of leave it unfinished. But I do know the measure of an exterior angle. I know that that's going to be 60 degrees. So if this angle here, one of my exterior angles, is 60 degrees, once again I can use this formula here for regular polygons, which is that one exterior angle times n, the number of sides in my polygon, equals 360 degrees. Well, in this case, I don't know the number of sides, that's what I'm looking for, but I do know the measure of one exterior angle. It's 60 degrees. So 60 times n equals 360. I can divide both sides by 60, and I get n equals 6, which means I must have a 6-sided regular polygon or a regular hexagon. So just given this information, I've managed to find, just given the measure of an exterior angle, I was able to find the number of sides in the polygon. Now there's one more example, example number 6. I want you to try this one on your own, and we'll take a look at this tomorrow in class.